Hello everyone! In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will revisit the double slit experiment. Alright, so at this point we're ready to return to the double slit experiment, and in fact we're ready to explain a result that is almost always introduced as revealing or epitomizing the strangeness of quantum mechanics. And what's interesting about our return to this is that we are now in a position to explain the full result, okay, in a way that fully makes sense if you have fully bought into the idea that what the electron really is represented by the wave function itself, and not the wave function being sort of a mathematical tool. So let's see what I mean here. Imagine you set up an electron gun, okay, so a hot filament with a potential difference applied, and conduct the double slit experiment for electrons, okay? What you get is that double slit interference pattern. And we're pretty comfortable sort of explaining why, right? The electrons themselves have a wave nature given by the de Broglie hypothesis, and that wave function that corresponds to those electrons is interfering, and therefore you get an interference pattern in the electrons that make it to the back. But notice that if you fire the electrons one at a time, you get the same result. And that is sort of one of the first mysterious results when this experiment was first conducted and first considered. But what is happening, right, now that we know a little bit more about quantum mechanics, is that the wave function corresponding to the electron, which really is the electron in an important sense, acts like a wave, and it behaves like a wave, and it travels like a wave, and it interferes like a wave, which means when it goes through the double slit, okay, it propagates out of the double slit as a wave that interferes would propagate. And then what happens is that when the wave function sort of strikes the back wall, okay, that back wall is effectively conducting a measurement, that it is forcing the wave function to make a decision about where that electron is. Notice that is anthropomorphic language there. It's not actually making a decision, but the wave function collapses when that wall interacts with the wave function itself, and the electron appears at one particular location. But if you conduct the experiment thousands and thousands and thousands of times, you realize that where that electron appears on the back wall is governed by the probability density pattern you would expect if that wave function is actually interfering. Okay, so any individual electron might appear anywhere on the wall, but with specific probabilities governed by what you would expect if that wave function were interfering with itself when it goes through the double slit interference pattern. And if you measure the wavelength implied by that interference pattern, both 1 and 2, you find that the wavelength is equal to h over p, the de Broglie hypothesis. And in sort of a classical frame of mind, you can, assume that you're still considering the wave function as sort of a mathematical tool, and you're sort of wondering, well, okay, the electron is really this little particle, but for real, which one did it actually go through? Like, I'm okay using that mathematical tool to calculate the result, but like the actual particle had to go through one of them. Notice how this question is only predicated on the assumption that the electron is a particle at all. But you ask that question, and so what happens if you put a detector next to one of the slits? That detector has a little potential difference and a little current, and that current is triggered if the electron goes through the right-hand slit, but not the left in this particular experiment. And so we can keep track of which slit the electron actually passes through. Well, if you do this experiment, one electron at a time, you end up with a classical pattern on the back wall, right? But now we have a full explanation for this. When that electron and the wave function corresponding to the electron reaches the double slit, the detector itself forces that electron to sort of be in one place by collapsing the wave function. right? So the location of the electron is measured and is with some probability in front of one of the slits and with some probability in front of the other, at which point that wave function continues to propagate onwards according to the Schrödinger wave equation, but without going through both of the slits. And so as a result, you get a very classical pattern on the back wall, having placed the detector here. Because the detector collapses the wave function at the moment of measurement so that the electron is firmly localized into a single slit. And so if you fully digest the idea that what the electron really is the wave function, and the wave function undergoes this thing called wave function collapse, when a particular property of that wave function is measured, then you get then you have a very straightforward explanation of what is otherwise a very mysterious phenomenon. And sometimes this phenomenon is made more mysterious by appealing to the idea that, like, how does this mysterious invisible wave function know that the detector is watching? How could it really know if there's a true observer or not? And that's a little misleading, okay? What counts as an observation is simply an interaction with another object or body that will depend on exactly where it is. That's it. That's what an observation counts as. And so in ordinary life, we almost never witness this behavior because there are a lot of things in physics which depend on the exact location of a particular particle. These kinds of isolated experiments are very rare. And so what is happening, the way that we experience the macroscopic world as having nothing to do with the wave nature of these objects, is because in those interactions, all of the particles that make up most of the things we interact with are constantly being localized into a particular point, okay? And that process of quote-unquote measurement, that is, that interaction, which depends on the property itself, is constantly occurring.